We're going to be going over sampling distributions. We're going to look at the population distribution versus the sampling distribution, the mean and the standard deviation of the sample mean, sampling distributions of the sample mean, the central limit theorem, and sampling distributions of the sample proportion. But first, we're going to start with talking about the sampling distribution of the sample mean and what exactly does that mean. So talking about statistical inference, well, first we have to use our data generated from a random sample or from randomized comparative experiments. We'll do a statistical analysis on that sample data, that is, to do measures of center and spread, look at its distribution. Then we'll use laws of probability to answer the question, what would happen if we did this a lot of times? Now, remembering what statistical inference is, we use information from our sample to infer something about the population. Reasoning rests on asking how often would this method give a correct answer if I used it very many times. So let's look at some sampling terminology. And we've gone over some of this terminology before. Parameter, a number that describes the population. In practice, this value is usually unknown. That's why we have to do statistical inference. So for example, we talked about the population mean and its symbol mu. We talked about the population standard deviation and its symbol sigma, and population proportion, p, as its symbol. Now statistics that estimate that parameter, now they're known values from a sample, and we've talked about the sample mean, which is represented by x bar, the sample standard deviation represented by s, and the sample proportion represented by p hat. So we have our sample mean, that x bar, our sample mean. It estimates mu, the population mean. S, the sample standard deviation, estimates sigma, the population standard deviation. P hat, the sample proportion, estimates p, the population proportion. So statistics come from samples, parameters come from population, and we use these statistics from the sample to estimate or to try to make our best determination of what the parameter for the population is. Variability. Variability is different samples from the same population may yield different values for the sample statistic. Sampling distribution tells what values a statistic takes on and how often those values occur in repeated sampling. So we already knew that a distribution is a variable value and how often it occurs. We talked about probability distributions. That is the variable value and the probability it would occur. Now sampling distributions tell us the statistic, the value of a statistic, and the probability it would occur. So a sampling distribution of a statistic is the distribution of values of that statistic that comes from a sample of a specific size from the population and the probability of it occurring. Now we're going to look back at the law of large numbers. We talked about it in several other situations. Now the law of large numbers says as the sample size increases, the sample mean gets closer to the population mean. That is, the difference between the sample mean and the population tends to become smaller. That is, it approaches zero as our sample size gets extremely large. Now we're going to use this to help us look at some of the things that are going to occur and some of the properties of the sampling distributions. So let's look at an illustration of the law of large numbers when we look at a distribution itself. So let's look at this very right-skewed distribution with a population mean of 2.56. If I take samples of size 25, they might not look exactly like the parent distribution that we just saw. But let's look at samples of size 1,000. Now that sampling distribution looks a bit more and much more close to what the population distribution looked like. So as we see, as our sample size increases, even our distribution starts to look more and more like the population distribution. So the larger the sample size, the better the sample estimates a particular parameter or characteristic of the population. So now let's continue on with looking at this distribution of sample means. In other words, creating the sampling distribution of the sample means for a particular sample size. We'll say n. So if we took sample 1 and we computed its mean from a sample of, let's say, size 10, and sample 2 and computed its mean, and sample 3 compute a new sample of size, let's say 10, and we computed its mean. So all of those were means that came from samples of size 10. We wouldn't have known what that mean was until we actually took it. Therefore, it makes x bar, the mean of samples of whatever size, a random variable. And as we know, each time we take a sample, we'll get a different number, so that creates variabilities. So we're going to have variability in that point estimate. That's the point estimate we're looking here is of the sample mean. Distributions of the sample mean. So from our population, once again, we're going to say we're going to take samples of size 10 and we're going to do it 15 times. So I take a sample of size 10, I calculate its mean, and I get 23.3. I take another random sample of size 10, calculate its mean, and it comes out to be 22.7. And I do this 15 times, and I get different sample means. I can actually create a distribution, and that would be the sampling distribution of the sample mean for samples of size 10. Now, the more times I do this, so let's say I did this not just 15 times, but I did it 1,000, I create a really full distribution that probably would look much more like what the sampling distribution of the sample mean for samples of size 10 is, a more accurate view. But something that we're going to find out is that our sampling distributions don't necessarily look like the population from which it came from. So we're going to take a look at an example. And I'm going to take an example of test scores, which are noted to be normally distributed. And I've got a population of size 5. And I take that population of size 5, and for each student, I take their grades, I add them up, I divide by 5 to get the mean, and then I take their standard deviation, which ended up being 8.888194417. It probably goes on and on and on. So it has a standard deviation of about 8.9. Now we're going to look for the first time at a sampling distribution for samples of size 2. And this is a complete sampling distribution, because I'm going to find every unique sample of size 2 taken from this sample, this population of size 5. So in this column right here that we see, these are all the different ways I could take the 5 people 2 at a time, because 2 and 1 is the same thing as 1 and 2. So all of these are unique. So what I did is I took person 1 who had a mean of 62, person 2 who had person 1 had a score of 62, and person 2 had a score of 80. So I took 62 plus 80, I divided by 2, and that's how I got 71. Person 1 and 3. So I took person 1 score 62 and person 3 score 58. I added those two, divided by 2, and that's where the 60 came from. So this column right here is the mean from each of the unique samples of size 2. So I've created a distribution, a sampling distribution of the sample mean for samples of size 2. And I have all the different means, and I could plot that and look at its distribution. And I could also find the measure of center and spread. So I added up all these means, which were 10 of them. I divided by 10, and I got a mean of 69. Now, as I note, that's the same mean of the population that I saw up here. Is that a coincidence? Or could that possibly be a characteristic of a sampling distribution? But when I look at the standard deviation, it's not the same. I see the standard deviation is 6.28, and this one is 8.89. They're different, and in fact, it's smaller. So we note that the standard error is smaller than the standard deviation. And you said, what, standard error? Well, that's what we call the standard deviation of a sampling distribution, the standard error. So instead of saying the sampling distribution, the standard deviation of the sampling distribution of the sample mean for samples of size 2, I say let's look at the standard error. And I know that I'm in a sampling distribution. Now, does this make sense that it should be less than the population? Well, that's where that law of large numbers comes in. The law of large numbers said the more in my sample size, the better the guess becomes. So my standard error becomes a little bit less. The standard deviation, that is, of the sampling distribution for samples of size 2, because my guess on the population mean becomes better and better. So let's take a look at the sampling distribution for samples of size 3. So I take person 1, 2, and 3, 62, 80, and 58. I add those three scores, divide it by 3, and I get the 66.6666667. I try to get as accurate as I could. And I did that for every unique sample of size 3 taken from these 5 students. And so now I create a distribution, and there just so happens that there's 10 unique samples of size 3. And I take the means of all those different samples of size 3, I add them, I divide it by how many there were, there happened to be 10. And once again, I say I get 69. And I'm starting to say, wow, I wonder, if this truly is some sort of a characteristic of a sampling distribution. And I note, once again, that the standard error even becomes less than the sampling distribution of the sample mean for samples of size 2. So it's getting smaller and smaller. But that does make sense. The law of large numbers would say my variability becomes less because I'm making better guesses. So now let's look at the sampling distribution of the sample mean for samples of size 4. So I take every unique way. I could take 4 people from the 5 students. This is every unique way. And then I take person 1, 2, 3, and 4. 62, 80, 58, and 72 divided by 4, that's where the 68 came from. And I did that for all the different samples of size 4. So now I've got the mean, all the unique means for samples of size 4. When I add up those means, divide by how many there were, and there are 1, 2, 3, 4, 5 different ways I could uniquely get 4 people from the 5. I get that the sample mean once again is 69. And I see the standard error is even smaller. So I'm wondering, what are these properties of the sampling distribution? Is it that the sampling distribution of the sample mean for any sample size will always equal the mean of the population? And does the standard error always get less as my sample size increases? And is there a set pattern to that, or a set relationship that I could know, which would be quite helpful? Now let's look at these distributions themselves. Now, in here, the population distribution is this black distribution. That's it's normally distributed, and those are for the 5 students and their test scores. Now, looking at the sampling distribution of the sample mean for samples of size 2, that's the red. You see the red arrow going into the red distribution? If you note, its variation gets smaller, so the distribution actually gets tighter, gets closer in. So I have more probability toward the center and less toward the end because I'm making better guesses at the mean. And then I look at the sampling distribution of the sample mean for samples of size 3. That's the green distribution you see here. And you see it's even getting tighter until we get to the sampling distribution of samples of size 4, and it's the blue one, and it's extremely tight and closer into the mean, which was 70, or 69, which is real close to 70. So I see that even my distributions, when I plot them, look tighter as my sample size increases, and they all center around the true mean of the distribution. So let's look at these patterns that we noticed with this example. The mean of the sampling distribution of the sample means always equaled the mean of the population from where those samples came from. The standard deviation of the sampling distribution of the sample mean were always less than the population standard deviation. And in fact, as my sample size increased, the standard error got smaller. The population was normal, and all the sampling distributions were normal. And we saw these patterns. And in fact, it is always true, and we can describe the exact relationship between the population and the sampling distribution of the sample mean for samples of size n taken from that population.